Welcome back. In this video, we're going to look at examples of finding the radius and interval of convergence for power series. Let's get to it. All right, so here's our first example. We want to find the radius and interval of convergence for the power series. And so here is our power series. We have the sum from n equals 1 to infinity of the quantity x minus 2 to the power of n divided by n squared times 4 to the power of n. All right, and so we know that this is a power series because it includes x raised to some power within it. In fact, we have x minus 2 to the power of n, and so we would say that this is a power series that is centered at the value of 2. All right, but that's not really going to be too important moving forward here, because what we want to do is find the radius and interval of convergence for this power series. And the way we're going to find that is by using the ratio test for series. The ratio test is going to allow us to solve for values of x that will make this power series convergent. And so that's what the interval of convergence will be. It's going to be an interval of x values for which this power series is convergent for. And so if you don't remember the ratio test, here's a quick refresher on what it says. For a series where we have the sum of a sequence a sub n, if the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n is equal to some limit L less than 1, then our series converges absolutely. Or in this case, we're just worried about the fact that it will converge, not necessarily that it converges absolutely. All right, but if that limit is equal to some value greater than 1 or it's equal to infinity, then our series diverges. And if the limit is equal to 1, the test is inconclusive. All right, and so essentially what's going to happen is that this value from our limit is going to involve x in some way, and so we're going to be able to compare x to 1. We're going to be able to solve for values of x that will make this limit less than 1 such that the series converges. And so that's how we're going to get our interval of convergence. All right, so that's how the ratio test is going to work. So if we go back to our example, for this power series, we are going to take the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n. All right, now in this case, a sub n is equal to x minus 2 to the power of n divided by n squared times 4 to the power of n. It's just this expression in our power series. Okay, and then a sub n plus 1 is going to be equal to this expression, but each n is going to be replaced with n plus 1. So we're going to have x minus 2 to the power of n plus 1 divided by n plus 1 squared instead of n squared, and then we're going to have 4 to the power of n plus 1. Okay, and so if we take the limit as n approaches infinity of a sub n plus 1 divided by a sub n, we're going to have this rational expression divided by this rational expression. All right, and so instead of writing out a very complex fraction of one fraction divided by another, I'm going to make it easier by just multiplying a sub n plus 1 by the reciprocal of a sub n, and that will be the same as dividing by it, right? Dividing by a fraction will be the same as multiplying by its reciprocal. And so this will be equal to the limit as n approaches infinity of the absolute value of a sub n plus 1, which will be x minus 2 to the power of n plus 1 divided by n plus 1 squared times 4 to the power of n plus 1. And we're going to multiply this by the reciprocal of a sub n. And so we're going to flip the numerator and denominator and have n squared times 4 to the power of n divided by x minus 2 to the power of n. Okay? And so now what we want to do is simplify this limit up to a point where we can evaluate it and see what values of x are going to make this limit less than 1, which from the ratio test would say that our power series converges. Okay, and so the first thing I'm going to do is break up our powers. We have x minus 2 to the power of n plus 1. We can break this up to be x minus 2 to the power of n times x minus 2 to the first power, and then we can break up this power as well and have 4 to the power of n times 4 to the first power. And so if we do that, this will be equal to the limit as n approaches infinity of the absolute value of x minus 2 to the power of n times x minus 2 to the first power, and then we'll have times n squared times 4 to the power of n, and that's all divided by n plus 1 squared times 4 to the power of n times 4. We just split up that power, and then we have x minus 2 to the power of n. Okay, And so now that we split up those powers, we have some parts that are going to cancel within this limit, right? We have x minus 2 to the power of n in the numerator and x minus 2 to the power of n in the denominator. So those are going to cancel out. And we also have 4 to the power of n in the numerator and 4 to the power of n in the denominator. So those are also going to cancel. All right, and so now what we're left with is the limit as n approaches infinity of the absolute value of x minus 2 times n squared divided by 4 times n plus 1 squared, right? That's what we have left in this limit. This quantity of x minus 2 and n squared are in the numerator, and then 4 and n plus 1 squared are in the denominator. Okay, so if I clean up my work, what we want to do at this point, now that we have simplified those powers and canceled some things out, I'm going to split up the parts of this limit. And what I mean by that is I'm going to group all of the n's and all of the x's and any other constant multiples, right? So what I'm going to do is pull n squared and n plus 1 squared out of the absolute value bars, because all values of n are going to be positive from 1 to infinity, right? Those are the values for which n is defined for. And so the absolute value bars aren't necessary for any of our parts with n in it, but they are necessary for our quantity with x, because x can be a negative value unlike n. So here's what I'm going to write. This is going to be equal to the limit as n approaches infinity of n squared divided by n plus 1 squared times the absolute value of x minus 2 divided by 4. All right, so I just split this up. We have our two parts with n on the outside of the absolute value bars, and then we left x minus 2 within the absolute value bars, and then kept that 4 down there as well. All right, now what we want to do is evaluate the limit as n approaches infinity for this expression with n in it, and we can totally ignore this part over here because this is the limit as n approaches infinity, not x, and so x minus 2 and 4 are not going to be affected by this limit in any way. You can treat this part of the limit as a constant multiple. So in order to evaluate this limit, I'm going to expand this denominator. So what we'll have is that this is equal to the limit as n approaches infinity of n squared divided by n plus 1 squared expanded. So if we want to square this quantity, I'm going to use a little trick here. We'll start by squaring the first term, so n squared is n squared. Then the next term will be these two terms multiplied together and then multiplied by 2. So we have n times 1, which is n, times 2, which is 2n. So we have plus 2n as our next term. And then the last term of the expansion will be this term squared. So we have 1 squared, which is just 1. Okay? And then we need to multiply this by the absolute value of x minus 2 divided by 4. We don't need the absolute value bars around 4 because 4 is always positive. And now we can evaluate this limit as n approaches infinity. Note that we have a rational expression where the numerator and denominator are both algebraic. And so what we can do is look at the highest powers of n in the numerator and denominator, and depending on whether they are equal or one is bigger than the other, we can make a quick decision about what this limit is. In this case, we have n squared as the highest power of n in the numerator and n squared as the highest power in the denominator. So since those highest powers of n are equal, they're both 2, the limit as n approaches infinity of this expression will be equal to the ratio of the coefficients for those two terms. All right, so this limit will be equal to this coefficient for n squared, which is 1, divided by this coefficient for n squared, which is also 1. So this limit is equal to 1 divided by 1, which is just 1. So this will be equal to 1 times the absolute value of x minus 2 divided by 4. Okay, and 1 times anything is just going to be that value, and so the absolute value of x minus 2 divided by 4 is the result of this limit. And so if I clean up my work here, what the ratio test tells us is that if this limit is less than 1, then our power series will converge. Okay, and so since we have this variable x, what we need to do is solve for x to determine the interval of convergence. What values of x will this power series be convergent for? And so what we can do is multiply both sides by 4, and if we do that, we'll have the absolute value of x minus 2 is less than 4. And then before we do anything else, right here at this step, we can now identify the radius of convergence for our power series, right? The moment that you have the absolute value of the quantity involving x that is being raised to the power of n from your original power series, whatever that is less than, that is the radius of convergence for your power series, right? So we had x minus 2 to the power of n in our power series, and now we have the absolute value of x minus 2, and that's less than 4, and so 4 is going to be the radius of convergence. And so from that, we can say that capital R, the radius, is equal to 4. Okay, so that's half of our problem. We found the radius. Now we need to find the interval of convergence. So let's continue on with this inequality. Let's solve for the values of x. Remember that the absolute value bars are essentially saying that this expression x minus 2 is less than 4, but greater than negative 4. Okay? Because if we're taking the absolute value of whatever x minus 2 is, all those negative values from negative 4 up to 0 would have become positive 4. All right, so if we remove those absolute value bars, then we just have x minus 2 greater than negative 4, but less than positive 4. Okay, so now if we add 2 to each part here, we can solve for x. And so negative 4 plus 2 is negative 2, and 4 plus 2 is 6. And so what we have here is negative 2 is less than x, which is less than 6. And so what this says right here is that when x is between negative 2 and positive 6, this power series will be convergent. If we pick some value of x between those two values and plug them in right here, the resulting series would be convergent. And so if x was negative 1, this power series would be convergent. If x was 0, it would be convergent. If x was 1, 2, 3, 4, it would be convergent. But what about negative 2 and 6 themselves, right? What about these endpoints? We know that our interval of convergence will at least be negative 2 to 6, not including the endpoints, because this is strictly less than. These are not less than or equal to signs, they're just less than. And so what we want to do to see if these endpoints are included as values of x for which this power series is convergent for is we need to test each of those values manually for the power series. So what I mean by that is we are going to plug in x equals negative 2 and x equals 6 separately into this power series and test the convergence of that resulting series. And so if that series is convergent, then we will change an open bracket to be a closed bracket to include that endpoint. But if the resulting series diverges, then we will leave the bracket as an open bracket. Okay, and so let me show you what I mean. If I clean up my work here, let's start by checking the endpoint x equals negative 2. When x equals negative 2, our power series will look like this. We'll have the sum from n equals 1 to infinity of negative 2 minus 2 to the power of n divided by n squared times 4 to the power of n, right? We just replaced x with negative 2. So now if we simplify, negative 2 minus 2 is a negative 4, so this is equal to the sum from n equals 1 to infinity of negative 4 to the power of n divided by n squared times 4 to the power of n. Okay, so now we can simplify this a little bit further. Notice that we have negative 4 to the power of n and 4 to the power of n in the numerator and denominator. So what we can do is combine them like this. We'll have the sum from n equals 1 to infinity of 1 divided by n squared times negative 4 divided by 4 to the power of n. Right, both of those parts were raised to the power of n, so we can just have that fraction raised to the power of n. And now, negative 4 divided by 4 is just negative 1. So we could rewrite this series again to be the sum from n equals 1 to infinity of 1 divided by n squared times negative 1 to the power of n. In fact, we could actually multiply that into the numerator, and then we would have negative 1 to the power of n divided by n squared. All right, and so now we have a series that we are familiar with. We can test this series using one of our previous tests for convergence. In this case, we have an alternating series because of this negative 1 to the power of n, right? That is going to make the terms of this series alternate between being positive and negative. And so we can test the convergence of this series by using the alternating series test. All right, and so the alternating series test says that our series will converge if two requirements are met. The first one is that the limit as n approaches infinity of the sequence from our series needs to be equal to 0. And remember that that sequence is not going to include the part that makes the series alternating. So instead of negative 1 to the power of n divided by n squared, we're just going to have 1 divided by n squared. All right, so we're going to look at the limit as n approaches infinity of 1 divided by n squared. Now for this limit, as n approaches infinity, we have 1 divided by n squared. And so as this n approaches infinity, we're squaring that value. So this denominator is increasingly getting larger. The denominator is approaching infinity. And so we have 1 divided by infinity, which we know is equal to 0. So this limit is equal to 0. So the first requirement of the alternating series test is met. And then our second requirement is that this sequence is a decreasing sequence. So what we need to show is that a sub n plus 1 is less than or equal to a sub n. In other words, the next term of the sequence is less than or equal to the previous term. That is what it means for a sequence to be decreasing. Each subsequent term gets smaller. And so is that true for our sequence 1 divided by n squared? Well, a sub n plus 1 will be 1 divided by n plus 1 squared, and a sub n is just 1 divided by n squared. And so will this term always be less than or equal to this term? Well, if we look at the denominators, we have n plus 1 squared versus n squared. This denominator is always going to be bigger than this denominator because we are squaring a value that is 1 bigger than n. So n plus 1 squared will be bigger than n squared. And when you have a bigger denominator for a fraction, the value of that fraction gets smaller. And so this fraction, or this term, will always be less than or possibly equal to this term. All right, so it's true that our sequence is a decreasing sequence. And so since both of these requirements are met, the alternating series test says that this series converges. All right, and so since this series converges, what we have just shown is that when x equals negative 2, this series is a convergent series. And so negative 2 should be included in our interval of convergence. So instead of having an open bracket, we're going to have a closed bracket. Negative 2 is included in the interval of convergence. Our series will be convergent when x is negative 2. Okay, so we checked one of the endpoints. Now we need to check the other when x equals 6. So if I clean up my work, let's check x equals 6. When x equals 6, we'll have the sum from n equals 1 to infinity of 6 minus 2 to the power of n divided by n squared times 4 to the power of n. All right, so we just replaced x with 6. And so if we simplify, 6 minus 2 is 4. So this is equal to the sum from n equals 1 to infinity of 4 to the power of n divided by n squared times 4 to the power of n. And now notice that we have 4 to the power of n in the numerator and denominator, and so those are actually going to cancel each other out. And so what we're left with is the sum from n equals 1 to infinity of 1 divided by n squared. And so this series that we have here is a p series, right? We have the sum from n equals 1 to infinity of 1 divided by n raised to a power of 2. And so this is a p series where p is equal to 2, which is greater than 1, which means that the p series converges. Okay? And so this series converges, which was the series that resulted when x equals 6 for the power series. And so since our series converges when x equals 6 should be included in our interval of convergence. And so this open bracket will become a closed bracket, and now we have our interval of convergence. It is from negative 2 to positive 6, including those endpoints. Okay, and so that's it for this example. We have now found the radius and interval of convergence for the power series. Okay, and one more thing to point out is that notice that this power series is a power series centered at 2, right? We have x minus 2 to the power of n. This 2 tells us that the power series is centered at 2, which you can see from our interval of convergence and the radius of convergence, right? Each of these endpoints is 4 away from positive 2. 2 plus 4 is 6, and 2 minus 4 is negative 2. All right, so I just wanted to point that out. It's kind of a neat thing that happens. Wherever your power series is centered, the radius tells you how far away from that center point your endpoints will be for your interval of convergence. Okay, and so with that, let's take a look at another example. All right, so here's our next example. We once again want to find the radius and interval of convergence for the power series. This time our power series is this series right here. We have the sum from n equals 1 to infinity of negative 1 to the power of n plus 1 times the quantity x minus 3 to the power of n divided by n times 3 to the power of n. Alright, so if we want to find the radius and interval of convergence for this power series, we need to use the ratio test. So we're going to look at the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n. Alright, so in this case, we're going to have the limit as n approaches infinity of the absolute value of a sub n plus 1. And so a sub n plus 1 will be this expression, but each n is going to increase by a value of 1. So we're going to have negative 1 to the power of n plus 1 plus 1. But that's just going to be n plus 2. So we'll have n plus 2. And that will be multiplied by x minus 3 to the power of n plus 1. And then we'll divide by n plus 1 times 3 to the power of n plus 1, because each of these n's needs to increase by 1. So this n became the quantity n plus 1, and this power of n became n plus 1. Okay? And now we're going to divide a sub n plus 1 by a sub n, or what we can do is multiply by the reciprocal of a sub n, and that will be the same thing, right? Dividing by a fraction is the same as multiplying by its reciprocal. And so this up here is a sub n, so we're just going to flip the numerator and denominator. So we're going to have n times 3 to the power of n divided by negative 1 to the power of n plus 1 times x minus 3 to the power of n. Okay? And so now we have our limit that we need to evaluate. The first thing I notice here is that these absolute value bars are going to eliminate negative 1 to the power of n plus 2 and negative 1 to the power of n plus 1, because both of those parts can only be one of two values. They will either be positive 1 or negative 1, and so the absolute value of that is always going to be positive 1. So we can cross those two parts out. The absolute value bars eliminate them. And then another thing that we can simplify are these powers for x minus 3 and 3. We can split those powers up, and that will make for some nice cancellation. So what we'll have here is that this is equal to the limit as n approaches infinity of the absolute value of x minus 3 to the power of n times x minus 3, right? We had x minus 3 to the power of n plus 1, so if we split that up, we have x minus 3 to the power of n, and then x minus 3 to the first power. And that is multiplied by n times 3 to the power of n, and then that is divided by n plus 1 times 3 to the power of n times 3 to the first power. We just split up this power right here, so we have 3 to the power of n, and then 3 to the first power. And then we are multiplying by this denominator, and so we have x minus 3 to the power of n. Okay, and so now we have x minus 3 to the power of n in the numerator and denominator, and so those are going to cancel out. And we have 3 to the power of n in the numerator and denominator as well, so those will also cancel out. And so what we're left with is the limit as n approaches infinity of the absolute value of x minus 3 times n in the numerator. So we have x minus 3 times n divided by n plus 1 times 3. So I have n plus 1 times 3. Okay, and so now, if I clean up my work, now that we have done a lot of simplification to our limit, the next step we want to take here is split up the n's from the x. All right, these absolute value bars aren't going to affect n or n plus 1 because n is always positive from 1 to infinity. And so what we can do is rewrite this limit to be the limit as n approaches infinity of n divided by n plus 1 times the absolute value of x minus 3 divided by 3. All right, we just split up this expression to have the parts with n on their own outside of the absolute value bars. And then we left x minus 3 and 3 within the absolute value bars. Okay, so once you do all your simplifying and canceling out, the next thing you want to do is separate n from x. And you want to get some expression like this, where the absolute value bars only have x within them and maybe some other constant multiple. Okay, because your next step is then to take the limit as n approaches infinity of the parts with n, because this limit only affects n. It doesn't affect x because this is a limit as n approaches infinity. Okay, and so for this limit, what happens to this expression as n approaches infinity? Well, notice that we have a rational expression, and both the numerator and denominator are algebraic parts, and the highest power of n in the numerator and denominator is the same, right? We have n to the first power and n to the first power. that is the highest power of n in both the numerator and denominator. And so since that highest power is equal, it's equal to 1, the limit as n approaches infinity for this expression will be equal to the ratio of the coefficients for those two terms. So this limit will be 1, the coefficient of this n, divided by 1, the coefficient of this n. So we have 1 divided by 1, which is 1, and so the limit is equal to 1. So we'll have that this is equal to 1 times the absolute value of x minus 3 divided by 3. Okay? And I just put the absolute value bars around x minus 3 only because 3 is always positive, so it doesn't need those absolute value bars. Okay? And so anything times 1 is just itself, so I can remove this 1, and we can just say that the limit is equal to the absolute value of x minus 3 divided by 3. All right, and so now this is the result of our limit for the ratio test, and so now what we can say is that when this value is less than 1, our power series will be a convergent series, because from the ratio test, when this value is less than 1, the series is convergent. All right, and so what we want to do is solve for the values of x such that this expression is less than 1. And so if I clean up my work here, if we multiply both sides by 3, we'll have the absolute value of x minus 3 is less than 3, right? And so at this point right here, we can now determine the radius of convergence for our power series, because we have the absolute value of x minus 3, right? The moment that you just have the absolute value of the part with x in it from your power series less than some value, that value is going to be your radius of convergence. In our power series, we had x minus 3 to the power of n, and now we have the absolute value of x minus 3, and it's less than 3. And so 3 is our value of r. The radius is 3. Okay, so now that we have found the radius, we need to find the interval of convergence. And so, remember, these absolute value bars are saying that x minus 3 is less than 3, but greater than negative 3. And so if we add 3 to each part of this inequality, what we will have is 0 is less than x, which is less than 6, right? Negative 3 plus 3 is 0, and 3 plus 3 is 6. And so when x is between 0 and 6, for this power series, this series will converge. All right, so as of right now, our interval of convergence is from 0 to 6, not including 0 and not including 6. We will need to individually check these endpoints to see if they should be included within the interval of convergence. Because this right here is only telling us when x is greater than 0 or less than 6, not greater than or equal to or less than or equal to. These signs do not include equals. They're just saying that x can be between these two values. All right, so we will need to check these endpoints just like we did for the previous example. And so if I clean up my work, let's start by checking x equals 0. When x equals 0, our power series will be the sum from n equals 1 to infinity of negative 1 to the power of n plus 1 times 0 minus 3 to the power of n divided by n times 3 to the power of n. All right, we just replaced x with 0. And now if we simplify, 0 minus 3 is negative 3. So what we have here is negative 3 to the power of n. And so since we have negative 3 to the power of n in the numerator and 3 to the power of n in the denominator, we can write this series to be the sum from n equals 1 to infinity of negative 1 to the power of n plus 1 divided by n times negative 3 divided by 3 to the power of n, right? Both of those parts are being raised to the power of n, so we can have this fraction where n is the power. Now, negative 3 divided by 3 is negative 1, so this is equal to the sum from n equals 1 to infinity of negative 1 to the power of n plus 1 divided by n times negative 1 to the power of n. All right, and so now what we can do is combine these two parts. We have negative 1 to the power of n plus 1 and negative 1 to the power of n. If we multiply these together, since they have like bases, we will add the exponents. So we'll have negative 1 to the power of n plus 1 plus n, right? So if I erase this part and just add another n, now we have negative 1 to the power of n plus 1 plus n, and those two n's will combine to become 2n, and so we'll have 2n plus 1 as the power of negative 1, okay? And so now this is where something very interesting happens. Negative 1 to the power of 2n plus 1 is actually always going to be negative 1, and here's why. no matter what value of n you plug in here, it's going to be multiplied by 2, which automatically makes it an even number, right? 3 times 2 is 6, which is even, and 3 was an odd number, and 4 times 2 is 8, which is also an even number, and so no matter what value of n we plug in here, this is going to be an even number, and then we're adding 1 to it, which will make it odd. So every single power of -1 for any value of n is going to be an odd power, which will always result in -1. So no matter what, this numerator will be -1, and so we would say that this is equal to the sum from n equals 1 to infinity of -1 divided by n. All right, and now what we have here is just a p-series, specifically the harmonic series with a constant multiple of -1, right? We just have 1 divided by n to the first power. And so this is a p-series where p is equal to 1, which means that the p-series diverges, okay? And so since this series diverges, which is when x was equal to 0, the interval of convergence for this power series will not include 0, and so we're going to leave this bracket open. This interval of convergence will not include 0. All right, so we checked the first endpoint. Now let's check the second one. Let's see what happens when x is equal to 6. So if I clean up my work, when x equals 6, we will have the sum from n equals 1 to infinity of -1 to the power of n plus 1 times 6 minus 3 to the power of n divided by n times 3 to the power of n. All right, we just replaced x with 6. And now 6 minus 3 is 3. And so we'll just have 3 to the power of n, right? So this is equal to the sum from n equals 1 to infinity of -1 to the power of n plus 1 times 3 to the power of n divided by n times 3 to the power of n. And now we have 3 to the power of n in the numerator and denominator. And so those are going to cancel each other out and leave us with the sum from n equals 1 to infinity of -1 to the power of n plus 1 divided by n. All right, and now what we have right here is an alternating series that we need to test the convergence for, right? We have -1 raised to the power of n plus 1. This is going to alternate between being -1 and +1, and so the terms of this series are going to alternate between being positive and negative. And so what we can do to determine if this series converges or diverges is use the alternating series test. Now at this point, maybe you recognize this series to be the alternating harmonic series, and maybe you know that that series converges, but if you didn't know, you would still want to check it using the alternating series test. And so let's check each of the requirements for that test that will make this series a convergent series. The first requirement is to check the limit as n approaches infinity of the sequence without the part that makes it alternating. So we're just going to have 1 divided by n, and this limit needs to be equal to 0 to meet the first requirement. And in this case, the limit as n approaches infinity of 1 divided by n is 0 because we have 1 divided by infinity, which is always 0. So this equals 0. And so the first requirement is met. And then we need to check the second requirement, which is that our sequence is decreasing. In other words, a sub n plus 1 needs to be less than or equal to a sub n. The next term of the sequence needs to be less than or equal to the previous term. And so I'm going to check that over here. A sub n plus 1 will be 1 divided by n plus 1, and a sub n is 1 divided by n. All right, now comparing these two terms, 1 divided by n plus 1 is always going to have a greater denominator than 1 divided by n. This denominator is always one value greater than this denominator. And so, since this denominator is bigger, the value of this fraction will be smaller than this fraction. And so a sub n plus 1 is less than or equal to a sub n. And so our second requirement for the alternating series test is met, which means that this series is a convergent series. And so I didn't really leave myself any room to write that, so I'm just going to erase my work here, and what we're going to say is that from the alternating series test, our series converges. Okay, and so since we found that this series is convergent, we know that our power series converges when x equals 6. And so 6 should be included in our interval of convergence. So we will erase this open bracket and change it to be a closed bracket, and now we have completed our interval of convergence. This power series will converge for values of x between 0 and 6, not including 0, but including 6. Okay, and so with that, this was the last example for this video. So if you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.